Hello and welcome everybody to a new video. This is it. We've done it. If you've been following this series, we've made it to the end of this odyssey, and I have in fact succeeded in my initial goal for this side project that has ended up taking an inordinate amount of time to complete. I have published my no STD Rust crate that allows me to read and write to an SD card in a very minimal fashion that is formatted with FAT32. So you can find this on crates.io called FAT32 RS. So I'll throw a link in the description. And yeah, that's it. We did it. We finally got here. So in this video, I'm going to talk a little bit about the Rust implementation. So we've already done some deep dives into how the file system works and talked through the reading and writing of it in Python. So I'm not going to recover that ground. I'm going to show some of the Rust implementation and a couple of little points where it differs. I actually did share this the crate already with the Rust community on Reddit, and I had one really great question which was about porting between the Python version and the Rust version and what were some of the little differences that I encountered. So I'm going to talk a little bit about that, and then I'll give you guys a little demo of it working on my STM32 dev board. So there's a couple of repos here we have as well. So these are also linked in the description if you want to check out the source code. I have obviously the source code for the library itself here, and then I also have the source code, which is a little demo application of the SD card logger running on my STM32, which uses the STM32 Rust HAL library, which is really, really good. So yeah, we'll talk about this a little bit later on, and I'll show you a little bit about how I actually did the implementation on the dev board to use the library. So with that said, let's have a little look at the actual code that we're running, how the crate works, and all that good stuff. So if we go to the app here, so this is pretty much the same as the Python app originally. Like the way I set it up, more or less the same. Source code, pretty simple. I've got the main kind of disk stuff here, which is it almost name for name. The functions are almost the exact same, aside from some side implementation details. I also have a folder for models, which again, almost like name for name model names, which were classes in the Python version. They're structs here in the Rust version with some implementation, some useful functions, mostly constructors and factory methods, that kind of thing. Again, testing, basically the exact same. We've got the tests. They test nearly all of the same things. Some of the tests are written slightly differently, just being a little bit more idiomatic in Rust, but basically test for the same stuff, and I use the exact same test image file. So the data that it's running against is identical, so it should, in theory, just provide more or less the exact same stuff with the same assertions. I tweaked some of how the test works slightly so that some of the assertions aren't exactly the same, but it was useful in building this that I knew I had a set of passing Python tests that I was able to look at the assertions of, so that I knew I had implemented this correctly, or at least as correctly as the Python version is implemented. So that was a nice little handy thing. Yeah, tester there. We can run our tests with just cargo test, which is very nice. There we go. Yeah, it's going to run our tests. There's one test that takes a few seconds to run, so it'll sit there while that runs. Interestingly, if anyone's interested, the test, it does the same thing. It's a load test that basically just tries to fill the disk by writing files to it and then appending to those files to just make it really big. And there we go, that's just completed. And overall, the entire test suite, including that load test, took 21 seconds to complete. Interestingly, more or less the same test suite with the same load test takes about 60 seconds to complete for the Python version. So seeing our little our performance improvement there with using the Rust version of this over the Python version. What else is in here? So structurally, I also am able to include examples in Python, or in Rust. So in the Python version, the examples are just Python modules that are provided with the source code, but Rust actually supports shipping specific examples with crates. So you can do this all with cargo. So you basically create an examples directory, fill it with these files, and these are just kind of standalone Rust files. They have a main function, and then in your cargo file you can actually define the examples in here as targets. So then when you go, you can type cargo run. So cargo run, if this was just a normal like executable target, it would just execute the target. For this, you go dash dash example and then provide the name of the example. So I can say append to file without the extension or s, because it just knows the name. And then, oh, that's not how you spell append. PPED. There we go. Append to file, enter, and there you go. That's just run that example for us, which is super useful. So yeah, that is some of the running. So I guess maybe I'll talk a little bit about some of the implementation differences. So honestly, not that much. I was kind of thinking that there may be a few differences, but one of the main ones that I did have was in my Surface, API Surface. There's a couple of things that I did in the original version, which I actually improved them in this version. So originally I had, let's see, if I go to this is the public part of the API, basically. I had, so read file originally in the Python version was, I called it read file in chunks. And basically what it was it was implemented as a generator in Python. Don't know what that means. It's not terribly important, but it's basically a way of doing sort of yielding results from inside a loop and being able to iterate over those results. It's kind of like an iterator, slightly different anyway, but obviously the generator pattern itself doesn't exactly work in Rust. So what I had to do is I had to implement this as an iterator in Rust, which is a little bit more complicated. I also changed it. So previously the reason why I don't call this read file in chunks anymore is that I actually changed it so that it doesn't return blocks of 512 bytes at a time into memory. You can actually just iterate through it byte by byte, which is what this now does. So this file content thing in here is actually an implementation of an iterator. So this is a struct, and then you implement the iterator trait for this struct. And basically what this is doing is so the way the iterators work is you call the next function here, or anything that say is able to loop through the iterator, but will under the hood call next on that iterator struct that you have. If it returns none, then it will end the iterations. If it returns some, then it'll try and do the next iteration, and it'll keep going until it gets a none. So that's basically what you have to implement, is you have to implement some logic that does lookups and does query stuff, and then return one instance at a time, or get the next one. So you can load stuff into memory and then go to the next one, and every time the iterator is called, you return some until it's exhausted, then you return none. That is, yeah, so that's kind of that. The only thing that's a bit tricky in this actually is because I've actually made this is like a nested iterator, which is kind of funky to deal with. You have to sort of manage the state in your head when you're dealing with like two iterators, and you have to understand what the state is. One thing that this does make you do so a slight difference with the generators. So when you set up a generator in Python, you basically declare just a bunch of variables and stuff, and then you create a loop, and then you put a yields block inside that loop, and then that yield block is what will get returned out of the generator when it gets called. So that kind of allows you to very arbitrarily write the code that's inside that without thinking too much about the state that you have to maintain inside it. So you can create some super inefficient generators, and you can make them have like all sorts of wasted iterations inside them, or wasted memory stuff inside them, and not really think about it, because it's just like you just write it and then just go, yield, yeah, great, done. That's it. I suppose this is somewhat of a generic comment as well about using Python versus Rust. is that you have to really think about what the data structure is all the time, because you have to define it quite, concretely. So with an iterator, you do have to define what all the state is going to be, because the idea is that the iterator itself, I don't want to say it's stateless, but it has to be able to know how to get the next piece of data for itself. So you have to be able to define some state inside it that it can then use to fetch the next piece of data each time. Maybe I'm splitting hairs on how that's much different to a generator or not, but in my head, this is more concrete. You have to put a little bit more thought up front into it. And it means you'll sort of, if you end up doing something that's a bit weird in there, you'll end up fighting yourself. So you sort of have to think it through a bit more to come up with a nice way of getting the data out. In this as well, I've got nested iterators in here. So I have this file pointer iterator here, which inside the file content. The file pointer iterator is effectively, the logic that's inside this is the same as the logic that is called by, in the Python functions, read file in chunks. So this file pointer will return you the blocks of 512 at a time, and then this iterator, which calls that iterator, chunks that up into individual bytes that you can then read out. So it's a little bit going on here. It's not necessarily super straightforward, but what it does do is it kind of splits up the logic a little bit. So as opposed to this complicated looping logic to fetch the data just being a function that's defined inside this module, instead it's functions that are implementations of traits that you're then going to operate with. So it's a little bit different, but it is quite clean because it's quite portable. Then the logic that's inside this can be used in other places very easily because it's just an iterator. So anything that can iterate this can consume the data out of it, which is, again, probably splitting hairs. I mean, if you just have a function that returns a generator, that's basically the same thing, just a little bit different. Okay, what else was different then? So we have this stuff. Oh yeah, so other thing that was different is how we have to actually define the read and write methods. So in our Python version, we basically wrote these closures that you pass in, and those closures then just do stuff. And like, because it's Python and it's all just whatever you want, pass in whatever you want, it doesn't matter. Python doesn't care, right? So it's just functions, and it'll just execute the function and then return something from it, and that's all that matters really. Within Rust, obviously, we can't do that. So Rust also, for my money, whenever I'm doing stuff, so I do a lot of kind of algorithmic programming in Rust. I think I talked about this before. I was obsessed with doing advent of code puzzles in Rust. And one of the things I found before is like trying to do things with closures and like sort of dynamic programming, creating functions that can be called based on keys that are stored in a hash or something like that. Not the cleanest pattern that you can use in Rust, but we can use actual language patterns that Rust has to achieve very similar thing in this case, and it works quite cleanly. So in this case, what we have done is we have defined this trait, which I've called block IO. So the idea being that this defines the input and output of a single block of data to the disk, which, if you remember, that's our implementation. Our whole cornerstone of our implementation of this is that if I have a block of 512 bytes, that I can read that, and that I can also write that 512 bytes to the disk. So I defined this trait. So if you're not super au fait with Rust terminology, a trait is effectively kind of like an interface, you can think of it as. I realize maybe if you come from a non-older school OOP background, maybe an interface doesn't make any sense to you either. But effectively all it is it's a definition, like a method signature that tells you what something should do, but it doesn't tell you how it should do it. So it's up to you then, when you implement that trait, to provide the actual implementation details in the middle of it that satisfies the requirements. But what you can do really powerfully then is you can type things in such a way so that you don't care about what the actual implementation is, you just care that it implements the trait itself, and then you can derive other functionality, and you can compose the functionality based on anything that implements this trait I can use to do X. And that's exactly what we've done here. So I defined this trait, it's a read block and it's a write block. I don't care how you read that block, what the underlying mechanisms you are to read and write to that block are. I don't need to care about those. All I care about is that I give you a byte offset and I give you a data block here, and that you'll return to me a result which will have data in it, or you just, in the right case, you just return to me a successful or a failure result. That's it. So the way this gets implemented then, so I can show you the implementation. I can show you the implementation that's like the standard implementation that is being run on my local machine and what gets run in the tests, and then I can show you how the implementation works on the STM32 microcontroller, because obviously it's different, which is the whole point of this, is that this would be portable and that any implementation will work. So let's have a look at how that works. So the way I can show you this is if we go to our tests. So our tests, say, have an instance of this disk. In this case, you'll see it's disk, and this, you haven't seen that before. So what is that? Well, let's look at the disk, back to the definition of disk. So disk is here, it's disk T, which is just how generics are specified in Rust. And it says that this disk struct can be constructed with any instance of T, so long as that instance of T implements the block IO trait. And then everything that happens underneath here will all work for anything as long as it implements the block IO trait, which defines the read and write block functions. So if I go into my test, into my tests, I have a helper here, which just sets up the disk for me, so I don't have to do it over and over again in every single test. So I have an instance of this, and you'll see here this is doing doing a static analysis to tell me that it's an instance of not an IO or block IO. It's an instance of a file-backed device, which the specific reason of that you'll see now. So we'll have a look, go into it. So this is just our test helper, just setting up the test for us. And here is the implementation for the trait. So I defined this thing, this file-backed device, which is using, it's basically just a little wrapper around a file. The file happens to be a temp file. The reason for that is so that I can, similar if you remember from the Python solution, I need to take my fixture, basically my disk image, and I need to copy it into some temporary directory so that I can mutate it between tests and it won't bork everything, basically. So it's a temp file and it's this file back device. And then I implement my read and write blocks for this file back device. And you can see how this works. So we have the read block. We know we need to pass it in this byte offset and return some results of bytes. So the way this happens, uses basically the underlying file implementation for Rust, which is this is an std implementation. Uses the standard library to access files. In this case, a temp file, slightly different, but basically the same. So what we have to do is we have like a seek. So we read to the seek position our byte offset, and then we create a little buffer. We read the data from that seek point with the size of the buffer, and then we return the buffered data, and that returns this, and that's it. And that's it. And our actual library code doesn't care about that. It absolutely doesn't care how it's implemented. All it knows is that, I'll just get the result from that function that I execute, done. And then the same with the write block, slightly different implementation, not really important, doesn't matter. But what's important is that the block has been implemented and the library code can call to that and do its thing on the platform that it's running, and that's all that matters. Doesn't care. So is there anything else then? So I want to show you, the next thing I want to show you is I want to jump over to that, the example I have of the running on the STM32. I'll show you the implementation and run it. show that it works. Just trying to think, is there anything else that's a little bit interesting or that I noticed different when porting between these two? Might come to me later, but I don't think so for now. Obviously, link is in the description to this repo, so you can feel free to go through this yourself. Well, caveat to say that I'm not a Rust expert of any kind. I just like this language and I'm learning it, and I'm kind of picking up bits and pieces as I go. There's a whole bunch of stuff in there that is absolutely not ideal, especially from considering I did say that this was intended to be used for an embedded system. The memory management isn't perfect in this, I wouldn't say. There's probably some optimizations that could be made to reduce the memory footprint, which would be obviously ideal in an embedded environment. And also there's a bunch of like lazy unwraps peppered through the code that sort of make assumptions about the way things work, which would obviously panic in if they unwrapped on, false results or nuns or whatever. So ideally I should fix those as well. I haven't fixed all of them. I fixed some of them. I haven't fixed all of them. So it's not necessarily 100% safe, this code. It's not unsafe, but I've made deliberate assumptions. So it could break in certain circumstances, but so far so good. The tests are all passing, so that's good. Okay, let's have a look at the STM32 example then. So this template, this is more or less a template that I've used for pretty much all my STM32 Rust projects. So some instructions here, how to set this up. It's all pretty straightforward stuff. It's not terribly complicated. If you are going to use stuff like this, it is quite bare bones. There is, what's it called? Embassy Rust you can use. So Embassy is a very well supported, really well thought out, really well designed embedded environment that exists for Rust. I haven't done much work with it, to be perfectly honest. I'm really enjoying doing some very low level stuff with this HAL library, which has really deep low level support for things, which I do enjoy. But yeah, anyway, just be warned, it's not exactly super user friendly, but I built this library to work with this, so you'll see the implementation now and it'll make sense anyway. But yeah, let's have a look at the main. It's a very simple program. It's all just setting up stuff. We set up the peripherals that we want to use inside the STM32. So again, this is somewhat STM32 specific stuff to do with how you set up like clocks and the devices inside. Might not be applicable. It's not applicable to all other types of embedded systems, but you will probably find similar stuff to this in different things. I set up the I/O pins, which will actually communicate with my device. So I have my breadboard is here, and it's an absolute rat's nest. But there's my where is it? That is the card reader, and it's got a bunch of wires to it, just going to the dev board itself. So there's just some GPIOs, and they are specific pins you have to pick, which are internally, these pins are wired to the hardware SDIO interface that is supported on the STM32 chip. That's another reason why I wanted to use this, why I had to do this, is because there are some other implementations of just normal comms with an SD card written in Rust already, but they particularly the one that I found, I can't remember the name of it now, name escapes me, but it's based around SPI. So I'd have to communicate with the SD card over SPI, that's fine. That's something you can do. But I did specifically for this case want to mess around with the SDIO hardware support, because I've just never used it before. And it happens to have a nice abstraction, which is natively part of the HAL library that I'm using, which is set up here. So all I do is I just need to know the pins that I'm using, and then I can set up the device here. Some other kind of boilerplate code here. So this just basically initializes the card, tries to communicate with it, and then it'll just succeed or fail. It'll kind of do some retries until it works. then down here, I can actually start using my library. So this is also just some other kind of boilerplate code. It just makes sure that at the very low level, I can actually read the card and guarantees that. So it just prints out a little message to tell me how many blocks, physical blocks are in my card. So this now is my implementation here. So it's very, very small, or this is my usage of my library. So I have defined something inside this, which is I'm calling my data logger. So I should say as well, sorry, don't think I said this at the start of this video. What I wanted to use this for, what the original impetus for all of this was, is that I'm going to be working on an embedded project where I'm going to want to log data out to an SD card in CSV files, basically. So I wanted to be able to just write line by line to an SD card, and then I want to plug that SD card into my computer, and I want to pull that data out and then do stuff with it. And this is something that I generally think would be useful for other projects as well. Especially something if you're using sensors, you want to pull sensor data out, you want to do some analysis on it on your computer. This is a very simple, straightforward way to set that up. So, this program it creates an instance of this data logger that is a module up here that I'll show you in a second. Passes in the SDIO module block that's defined up here. Then we loop through the numbers 1 to 100, and we output the value, the square, and the cube of that value. We do that 100 times. We write it to the card, check that there's no errors, do a delay, and then print a message. That's it. So it'll just write a bunch of numbers to the card, and that's it, appending to the end of a file. So let's have a look at how it does that. So if we open up our data logger, keep that open, and then we open up our data logger, you'll see our implementation. So I'm importing my FAT32 ORS crate. Then I define the data logger itself. So this is a struct that contains the disk and a file pointer to a specific file. You'll notice that whereas previously we were implementing a disk and a file backed device, now we're not. Now we're implementing a disk with an SD card backed device. So the SD card backed device is defined down here. So it's a struct. It is a little wrapper around an SD card, which is my SDIO SD card implementation, which comes from the HAL crate. Then I have the implementation for the block IO for the SD card backed device. And this does read and write. It's also super simple. It basically does some little bit of maths just to figure out what block addresses it needs. Then it calls to the SD card. It calls the read block method on the SD card, passes in a buffer, and then it returns the data from that block and does some error handling as well. And then the write is also quite simple. Has the passing the offset, does some stuff with some maths, and then it calls to the SD card's write block method, passes in the data, and the block does mirror mapping, returns the result. So it's very similar to the file IO that you saw from the previous example, but importantly, it's not the same at all. And it also doesn't care. So the library doesn't care that this is different to what the other implementation was. It just knows that when I execute this method, I'm going to receive this data, and then I can do everything else that I need to do with that data, and that's it. And that's the real beauty about this. And the important part about it being no STD rust is that this is perfectly portable. There's no dependencies. So my STM32 board doesn't have a standard library because it doesn't have an operating system or anything. So it needs to not make very many assumptions about what's running underneath the hood. So if my library doesn't make any assumptions, which it doesn't because it's also no STD, I can use this basically anywhere. And so here I've got, again, all no STD code in here. It does everything it needs to do. And then, but then, like we saw earlier in our previous example, I was using STD standard library code, and it still worked. So that's the real beauty and the real power of doing it this way. Very portable. So for the rest of this, nothing super interesting. not going into huge detail, but basically I can create this logger device. I pass in the SD card. I spin up the SD card back device. I instantiate the disk. I initialize it. And then I do some stuff in here. So basically what I'm doing is I'm looking for a file named log. If I find that file, if I don't find that file, I'll create it. If I find that file, I then will set that as the file for the logger that's up here. Then every time I call this, where is it? Where's the function? Oh, how did I do that? Oh, sorry, I don't do that. Sorry. My bad. I create the logger, and then how do I use it? I've forgotten how my own code works. What do? I go, so I have the logger implementation, create the data logger. Oh yeah, sorry, I do have a log method. I was just being blind. There it is, log method over the top. So this is for inside the data logger implementation. I have this log method. All it does is it pulls the disk instance and calls the append to file with the file reference. It's also defined up here and the data that gets passed in. That's it. Very simple. So when this is initialized and it's up and running, every time you call this method, it will just write that. It'll just write to the file, append to the file that that is set up in here, and that is this file named log, and that's it. So let's do it. Let's run it. Let's demo it working. So I'm going to have an SD card in here. I'm going to pop it into my little breakout board, and then I'm going to plug my programmer into the computer. Oh, sorry. Okay, and then up here, so I can use my cargo tools to do this. So just call cargo embed, hit enter. So it's going to compile it, upload it, and then it'll run it. So that's detected the number of blocks. There you go. So this is executing this program. Starts up, configures the clocks, waits for the card, finds the card, writes out the number of blocks that's on it, which is this, which should correspond to 8 gigabytes basically if you multiply it by 512. And then it has written the data to the card. I have this little delay in here as well, because so specifically I'm running this at a very low frequency. You can run this up to like 24 megahertz, but my clocks can't really handle it, so it kind of breaks down a little bit. So I'm running it quite slowly. It's also could be physically to do with the wires that I have, the janky little jumper wires I have. Could be just like could be breaking up. So I'm running it with this little delay for this example. So it takes some time to write to it. It also takes time to write to the disk in the first place anyway. It's not super fast. So one thing I may do with this is I may implement some buffer type situation so that every time you call it, it doesn't just try and write to the disk, because that could slow down what's going on. So instead I might create a buffer of sorts and then have some predetermined amount that it'll write and then splat that out periodically, so it's not just always doing it all the time. See about that. That's a future thing. So that's written the content. This file, this program then just hits a loop here. That's just a no-op loop to just sit there forever doing nothing. So I can kill that program there, or just kill my RTT debug terminal. It's not gonna do anything anyway. And then let's have a look at the log file that we wrote. Plug this into the computer. Oh, a second. Okay, so we'll open up the Finder. There's the SD card. I called it logger. It has a few files on it. Log is the file that we are interested in. So it's already got some data in it. It's got 5 kilobytes. So if I drop that into my text editor here, there's our data. So it's it's the value I from 0 to 99, then I squared and I cubed. And what you'll notice is I've written to this file a few times. So there's the first 100 values there written to the file, and then you'll see where I wrote it again. So it's basically keeping what's in the file and just appends to it each time. And so we see it again, and again, and that's it. So this was the last time I did it, which was just now. So this is the last 100 lines appended to the file, and this will just obviously keep going. And I can delete the contents out of this file, like plug it back in and run it, and it'll do the same thing again, and then again, and I can always get the data back out of it. I could also start to, increment a number. So I was kind of messing with that here. You see this file here called log n. So if I could have like an incrementing integer, then I could check, oh, what was the last integer? Create a new file that's now called log 1, log 2, log 3, log 4. And then each time the program boots up on the board, it'll create a new file, and that'll be the log file for that run. So I could do that as well. Okay, that I think is about it. This has been 36 minutes so far. If you guys are still watching, amazing. I commend you deeply. But yeah, that's pretty much everything I wanted to talk about. This has been a bit of a trip. It's been kind of an odyssey, and I'm really, really happy that I stuck with it and kept doing it. I was really enjoying doing it. This is the type of programming and problem solving that like really stimulates my brain. It really gets me thinking, which I really love doing that kind of problem solving. So I was really happy that I kept going with this. There's a whole bunch of stuff that's not implemented here. I don't handle long file names, which is a thing in the proper FAT32 file systems. I don't handle deleting files. I don't handle, just tons of stuff, loads of stuff. I don't handle directories properly. I just have one directory, which is the root. Can't do anything else outside of that. So yeah, there's a lot of limitations to this, but as I've just demonstrated, what I have can do this, and this is what I needed it to do. So I wrote it very specifically to do this job, and it seems to be doing it pretty well. So I'm very happy with it. I will probably expand on this implementation, like I said, with maybe integer names. Maybe I'll write some other stuff around this that can append, timestamps to the things that you log to it, all that kind of stuff. Obviously, I don't have full timestamps, but maybe just an incrementing, like a timer counter thing that I can use from the clocks that are on the chip. But yeah, for now, this is what I needed to do. I'll keep working on this stuff because this is going to be really useful for me to have just lying around, code I can refer back to and use in different places. And yeah, I think that is it for now. So thanks for staying with me if you're still here. Thanks for watching the other videos. Hopefully if you've checked them out in the playlist. And yeah, just thanks for being here and enjoying me talk about all this random stuff. I'm going to leave this here. I think the next projects I do, I'm not entirely certain what the next thing I'm going to work on is. I alluded to this embedded project I am working on. There's some hardware stuff I need to do next, so I might do that, document it, make a bit of a change from just this pure code stuff that I've been doing more recently. But I have something else that's going on in the background. It's kind of a bit bigger that I was hoping to be able to talk to you guys about already, but I can't yet. Still can't. I've mentioned this before. I'll be able to talk about it soon. I swear, I promise. Won't leave you guys waiting too long. But yeah, let's leave it there for now. As always, thank you guys for watching, and I will see you in the next one.